Good day. This is the PowerPoint about buffers. So the function maintain a relatively constant pH even if a major stress is applied. This is important in the world of biology. For example, your blood is buffered. It's important in many chemical applications, and that may include making medicines and things like that. So the stress we're going to apply is either adding strong acid or strong base, H plus or OH minus. Le Chatelier's principle comes back. So since Le Chatelier's principle is part of the game, we can only have buffers if we have a weak acid, weak base buffer. It cannot work for a strong acid or a strong base because they go to completion. We don't have an equilibrium. So here's a sample of what we might run into. Let's say we have a fair amount of acetic acid, no problem with the water, but we know when we normally have this, we have lots of acetic acid, but we're not going to have much of the acetate ion. So now we want to see how does it react to adding acid and base. So let's look at this equilibrium. When we add OH minus, it goes after the H3O plus. It's going to make that concentration go down. Now, Le Chatelier says we want to keep things the way they were as much as possible. We want to oppose that stress. So if H3O plus is going down due to stress, we want to do something to have the H3O plus go back up. And that means the equilibrium shifts to the right. Because we have lots of the acetic acid, no problem. So adding some amount of OH minus, this equilibrium can handle that. But let's see what happens if we add H plus. If we add H plus, we know that really is increasing the H3O plus. And Le Chatelier says, well, if that went up, we want to go back down. Hey, we're going to make it shift to the left to use some of that up. Our problem is we don't have much acetate ion. So as soon as all of this acetate is reacted, there's no more acetate for the H3O plus to react with, and it will simply pool, and we don't get that shift. So this equilibrium as written is buffered for the addition of OH minus, but not buffered for the addition of H plus. Now you might say, hey, the solution looks pretty obvious. We know lots there is good, and if we make this lots, then that's going to be good as well. And that's exactly what we're going to do. So it says can resist the changes by OH but not H plus. In order to be able to handle both kind of stresses, we are going to go with lots and lots. There's our lots and lots. Now, nothing changes for the OH minus, still applies. Because we have lots of CH3COOH, it has no problem shifting to the right. But now we have lots of this, the acetate ion. So if we have the addition of H plus, and we want to use some of it up and shift left, now we have plenty of this to react and shift it over. And a buffer is going to be good until we run out of either the conjugate acid or the conjugate base. Once we run out, it's no longer buffered. Let's see how this, that's a real mess. So the equilibrium can now resist changes in pH caused by addition of OH minus and H plus up until the point it runs out of either the conjugate acid or base. So buffer needs to be an equilibrium system, a weak acid, weak base. We have acidic buffers, basic buffers, and we can control our buffers by varying the amount of conjugate acid and conjugate base. So it talks about blood, your blood's buffered, preparation of food, antibiotics, things like that. What other mumbo jumbo? Now this is a titration graph I stole, but it was to illustrate that this area here would be said to be buffered because we know we're adding lots of acid and the pH is changing very little. Where we have this massive drop, that area is called unbuffered. These are great words. And that's because it cannot handle the addition of more acid without a big change in pH. So it reminds us where the graph is flat, said to be buffered, and the pH not changing much. And there's the unbuffered where it changes rapidly, and we are drawing to a close on this. Could you figure out how to calculate the pH of a buffer? That would be fun. And once you know that, then you probably can create a buffer of a certain pH. So that's a good place to end our look at buffers.